Hello everybody, this is Saqib Alauddin, physics and chemistry instructor, and this video deals with some questions related to AS level equilibria. Okay, question number 1. Ammonia is manufactured from nitrogen and hydrogen using Haber process. The equation is given. They say what is the expression for Kc of this equilibrium? Okay, remember Kc is the concentration of the products upon the concentration of the reactants, but be careful that there should be no solid in your expression because solids are not included in the expression of Kc. So concentration of product upon concentration of the reactant, the states are gas for ammonia, gas for nitrogen, gas for hydrogen, and do not remember to raise to the power of the coefficients. Now 2 is the coefficient for ammonia, so you have to write 2. 3 is the coefficient for hydrogen in the equation, so 3, and of course 1, so you write 1 or you don't write, that doesn't matter. So look at all the options and see which one is correct. Of course, you can see option number, you can see in this option number A is incorrect, option number B of course isn't. Look at option number C and option number D. The only difference in option number C and option number D that I can look for is actually, okay, there is a plus sign here, so it's a multiplication sign, so the answer is D. The option for this is D. Okay, question number 2. The reaction between sulfur dioxide and oxygen is reversible. So we are given this reaction. Which conditions of pressure and temperature favor the reverse reaction? Okay, now remember that delta H of the reaction is negative. That means the forward reaction is exo and backward reaction of course is endo. Okay, let's deal with temperature first. Remember, according to Chatellier's principle, when you increase the temperature, the endothermic side, which is the backward side, is favored. So when you increase temperature, that means the temperature becomes high. The backward reaction, the endothermic reaction, the reverse reaction is favored. So it's either option number A or it's option number C, because so option B and option D goes out of question. Because according to Chatellier's principle, when you increase temperature, endothermic reaction, which is reverse in this case, is favored. Okay, now let's deal with the pressure thing. See, remember, for gases, it is said that now all three are gases. Mind it, all three are gases. The total number of moles of the reactant gases are 3. The total number of moles of product is 2. So what are we saying? In this case, it says when you increase pressure, equilibrium shifts towards the side with less number of moles. So when you increase pressure, it will shift forward. Now in this question, they say backward. So it's the other way around. When you decrease pressure, it shifts towards the side with more number of moles. So if you want the backward reaction to be favored, what you need to do is to decrease the pressure. So pressure should be low. The answer should be C. I repeat, when you increase the pressure, equilibrium shifts towards the side with less number of moles. But when you decrease the pressure, it shifts towards the side with more number of moles, and on the reactant side we have more moles. So it will shift backwards. Remember, this is only applicable to gases. So option number C is correct. Question number 3. Which statement about the effect of a catalyst on reversible reaction is correct? Now, the correct option is B. The composition of the mixture stays the same. Remember, activation energy is lowered, so A cannot be correct. Rate of backward reaction stays the same, not necessary. Rate of backward reaction may also increase. And the value of equilibrium constant changes, that's absolutely wrong. No, the value of equilibrium constant remains unchanged when you add a catalyst. So answer is B. Question number 4. Now I'll just enlarge the screen so you can read this question. Graphs can be drawn to show the percentage of ammonia at equilibrium. At equilibrium is a keyword. When nitrogen and hydrogen are mixed at different temperatures and pressures. Which graph correctly represents these two graphs, which means the effect of temperature and effect of pressure. So what actually they are saying, that when this reaction is in equilibrium, now remember, ammonia is made from nitrogen and hydrogen, and it's a fact that the reaction is exothermic. You need to remember this, that this reaction is exothermic. So they are saying, what is the effect? Of course, on the percentage of ammonia when you change the pressure and when you change the temperature. Okay, let me count out some options. See, first thing, in all reversible reactions, remember, you need to see the total number of moles of the reactant. So there are 4 moles of gases on the reactant side, and there are 2 moles of gases on the product side. So increasing pressure, when you increase pressure, it should shift equilibrium forward. Why should it shift equilibrium forward? Because less number of moles, because of less number of moles of product. So Le-Chatellier's principle can be applied in a way that when you increase the pressure, equilibrium shifts toward the side with less number of moles, which means the percentage of ammonia should increase when we increase pressure. So in other words, we can say percentage of ammonia should increase. Okay, now should increase. Look at the options. In A, as the pressure is increased, the percentage of ammonia is decreasing, so A cannot be our option. Similarly, in B, the pressure, see, you can see the pressure is increasing, the percentage of ammonia is decreasing, so B cannot be our answer. So we are left with only C and only D, right? Because in both the cases, as you increase the pressure, as we see the pressure is increased, the percentage of ammonia is going up. Okay, now the second factor. Since the reaction is exothermic, which means the forward reaction is exothermic and the backward reaction is endothermic. Okay, so now if I want to increase the percentage of ammonia, I need to favor the forward reaction, which is the exothermic reaction. Now remember, at high temperature compared to at low temperature, what's the difference? When you increase the temperature, when you make the temperature higher, the endothermic reaction is favored. So in this, the endo, that means the backward is favored. Backward is favored. On the contrary, when you decrease the temperature, the exothermic, so in this case the exo, that means the forward reaction is favored. Now that's what I want. I want the forward reaction to be favored so that more ammonia can be produced. So what I need to do, I need to decrease the temperature, or I need to operate at a lower temperature. So the exothermic side, that means the forward side, is favored. So in this case, you can see at a lower temperature, of course, the percentage should be greater. And at a higher temperature, we can see the percentage should be lesser. So option number D is correct, because at lower temperature, you expect more percentage of ammonia, and at a higher temperature, you expect less percentage of ammonia. It's the other way around in option number C. So option number C is wrong, because in this, at a higher temperature, there is larger percentage. And at a lower temperature, there is lesser percentage, which is wrong. So option number D is correct. Question number 5. X and Y react together to form Z in a reversible reaction. The equilibrium yield of Z is lower at a higher temperature. Now, which means, remember I told you, whenever you have a reversible reaction, Z is in the product, okay, and X and Y are on the reactant side. Now, irrespective of the number of moles, if we say that the yield of Z is lower at higher temperature, which means when you increase temperature, it shifts backward. Backward reaction is favored. Remember that backward reaction is favored, because then only the yield of Z will be lower. If the reaction is shifting backwards, only then the yield of Z will be lower. Now, the fact is, when you increase the temperature and you always expect the endothermic reaction to be favored. So which means the backward reaction is endothermic, and which in other word would mean the forward reaction will be exothermic. Remember, when you say you increase the temperature, whenever we increase the temperature in a reversible reaction, according to Le-Chatelier's principle, the endothermic reaction is favored. And in this case, the backward is endothermic, the forward is exothermic, and hence we say that the delta H for the reaction has to be negative, because the delta H is actually for the forward reaction. So either option number A is correct or option number C is correct, which tells me that B and D are out of question. Okay, now about pressure. It says the equilibrium yield of Z is lower at lower pressure. Okay, which means we know for pressure, that means when you apply pressure to gases, if you want the yield of Z to be lower, the reaction should have more number of moles on the reactant side. Remember, see, in this case, option number A, I'll explain you with this example. Option number A, there are 2 moles of the reactant gases, and there is 1 mole of the product gas. Now, the rule says as we decrease the pressure, equilibrium will shift towards the side with more number of moles. In this case, equilibrium will shift backwards, and that is what we want, because as it shifts backwards, the yield of Z will be lower. So in this case, A becomes my answer. Why? Because you have more moles on the reactant side, you have less moles on the product side, and when you decrease the pressure, equilibrium shifts towards the side with more number of moles, that is backward in this case, and that is what we exactly want, because as it shifts backwards, the yield of Z will be lower. So option number A is correct. Option number C is wrong, because you see there are 2 moles on the reactant side and there are 2 moles on the product side. So in this case, when you decrease pressure, you will not see an actual shift in the backward direction. So that means option number A is correct. Question number 6. Now in this question it says, at high temperature, steam decomposes into elements according to the following equation. The equation is given. In one experiment at 1 atmospheric pressure, 20% of the steam had been converted into hydrogen and oxygen. 20% of steam had been converted to hydrogen and oxygen. The question is asking, what are the values of equilibrium partial pressures in atmospheres of the components of this equilibrium? Okay, now, first, what I need to do in this question is to find the moles at equilibrium. Okay, I need to find the moles of H2O at equilibrium. I need to find the moles of H2 at equilibrium and of O2 at equilibrium. Then only I'll be able to determine the partial pressures. Now this statement is very important, that 20% of steam has been converted. See what is happening here. In this I've made a sort of a table where this is initial amount, this is amount reacted, this is amount produced, and what is most important is the equilibrium amount. Okay, see, in the question it says that it was found that 20% of steam had been converted. Nothing else is given in the question. No other information is given. So what I assume is, say I'll take the amount of water initially as 1, and since it says 20% is converted, so what I'll do is, this is given in the question that 20% of 1 is 0.2, right? You calculate 20% of 1, it's 0.2. So 0.2 is the amount of H2O that is reacted. Okay, what I'll do is, in the initial amounts of H2, I'll put a dash. There wasn't any initial amount of H2. There wasn't any initial amount of O2. Okay. And also in amount reacted, I'm putting a dash because initially they do not react. Okay. So what happens now? See the ratio. You understand that the ratio is 1:1. So if 0.2 moles of H2O had reacted, we would expect 0.2 moles of hydrogen to be produced, because 2 moles of water when reacts form 2 moles of hydrogen. So you can see the ratio, it's 1:1. So if 0.2 moles of H2O had reacted, they'll produce 0.2 moles of hydrogen. On the other hand, the ratio is 2:1 with oxygen. So if 0.2 moles of H2O reacted, they will produce 0.1 moles of oxygen. So what do we have at equilibrium? See, initially we had 1 mole of water, 0.2 reacted. So how many remained at equilibrium? 0.8 moles of water remains at equilibrium, because it says 20% reacted. So at equilibrium you will have 0.8. Achha. In this case you will have 0.2 moles, because initially there was nothing and 0.2 were produced. So at equilibrium you will have 0.2 moles of hydrogen and you will have 0.1 moles of oxygen at equilibrium. So these are the amounts which we have at equilibrium. Okay. Now, partial pressure. Partial pressure of any gas is the moles of gas divided by total moles into total pressure. Okay, so I'll put it in simple: mole of a gas divided by total moles into total pressure. Okay, now let's do it for, say, I'll start with steam. Okay, what are the equilibrium? The sum of all of them, by the way, is the sum of all the moles would be 1.1. Remember, sum of all the moles. So now for steam, I'll do it for steam. So what is the partial pressure of steam? The moles at equilibrium 0.8 divided by total moles 1.1. And what is the total pressure? It's given in the question. The total pressure, it says 1 atmosphere is the pressure. So into 1. Right? Look at the options now. You will see which one is correct. Option number D. 0.8 into 1 divided by 1.1. All other options are wrong. And see, it's also true for hydrogen and also true for oxygen. See the equilibrium moles of hydrogen, 0.2. So 0.2 divided by total moles multiplied by the total pressure. It's also true for oxygen. See the equilibrium moles, 0.1. 0.1 divide by the total moles multiplied by the total pressure. So option number D is correct. Question number 7. Now, this is a reaction given for decomposition of nitrogen dioxide. Equation is given. Look at the data given. When 4 mole of nitrogen dioxide were put in 1 dm cube container and heated to a constant temperature, equilibrium mixture contained 0.8 moles of oxygen. What is the value of equilibrium constant Kc? Now, before we calculate the equilibrium constant Kc, we first again need to know the equilibrium amounts of all reactants and products, because in the expression of Kc you need to put the equilibrium amounts of the reactants and products. So let's start doing this. Now it says you had 4 moles of nitrogen dioxide. So initially we had 4 moles of initial amount is 4 moles of nitrogen dioxide, and we had nothing of NO and nothing of O2. Okay, what else? It also says the equilibrium mixture contained 0.8 moles of oxygen. So at equilibrium we had 0.8 moles of oxygen. Okay, now remember, since we had absolutely nothing initially of oxygen and at equilibrium you have 0.8 moles, so remember all 0.8 moles were produced during the reaction. So what I've done is I've written 0.8 moles of O2 being produced. Okay, now look at this. The ratio of oxygen and NO2 is 1:2. So if 0.8 moles of O2 are produced, double the number of moles of NO will be produced, because remember, when 2 moles of NO are produced, 1 mole of O2 is produced. So if we had 0.8 moles of O2, then of course 1.6 moles of NO would have been produced. Okay, I'll just put a dash in front of produced when it comes to the reactant. Okay, see now again, see the ratio. The ratio in for NO and NO2 is 1:1. I mean 2:2 means 1:1. So if we say 1.6 moles of NO are produced, then how much of NO2 reacted? I repeat, if 0.16 of NO are produced, then how much of NO2 is reacted? 1.6 moles of NO is reacted, because remember, when 2 moles of NO2 reacts, they produce 2 moles of NO. So Zahirat, that means 1.6 moles of NO2, when they would react, they will produce 1.6 moles of NO2. Okay, I'll put a dash here in amount reacted in front of the product. So how much of NO2 at equilibrium? Simply, you had 4 moles initially, 1.6 moles reacted. So what are we left with? 2.4 moles of NO2 at equilibrium, and of course 1.6 moles of NO at equilibrium, because initially there was no NO, 1.6 of NO was produced. So at equilibrium, these are the amount of moles at equilibrium of NO2, NO and O2. Okay, now the expression for Kc. Kc is concentration of product. So Kc is concentration of products upon concentration of reactants raised to the power of the coefficient. So concentration of O2 into concentration of NO, you have to raise it to power 2 upon concentration of NO2 to the power 2. Remember, concentration of the products upon the concentration of the reactants raised to the power of the coefficients in the balanced equation. Okay, now remember, they say that the total volume is 1 dm cube. Okay, let's determine the concentration of NO. NO, the concentration is moles upon volume, moles at equilibrium. Remember, in Kc we put amounts at equilibrium. So what are the moles of NO at equilibrium? 1.6. So I can say it's 1.6 upon the volume is 1 dm cube. The question says that 1 dm cube of container. Since all are gases, therefore the total volume of each gas will also be 1 dm cube. Okay, So this is 1.6 upon 1. For O2, this is 0.8 upon 1. And for NO2, it's 2.4 upon 1. Now you can see you can leave out 1 because when you divide something by 1, it remains the same. So simply concentration of NO square into concentration of O2 divided by concentration of this. So that's the expression of Kc. You can see which option is correct. The only correct option that is option number D. 1.6 square into 0.8 divided by 2.4 square. Okay, question number 8. Now I'll just enlarge the image so that you can clearly read the question. Now it says there is a reaction given. You can see in this reaction X converts to 2 moles of Y. Both are in aqueous state. Now the question says a solution of X has initial concentration of 0.5. When equilibrium has reached, it has fallen to 0.25. Okay. Now let's see. See, once again, I'll quickly do some calculation to make you understand. Okay, initial amount, I'm writing initial amount as IA is 0.5 of X and nothing of Y. Okay, now it says, this is amount reacted, AR for amount reacted, AP for amount produced, and EQ for equilibrium amount. Now it says when equilibrium has been reached, it has fallen to 0.25. So equilibrium is 0.25. Remember, if I say the equilibrium amount of X is 0.25, that means how much of X you think would have reacted. Now 0.25 is the remaining amount. So of course you subtract 0.5 was the initial amount, you subtract 0.25 which is the remaining amount, so that means 0.25 is reacted. Okay, so the amount of X that had reacted is 0.25, and if 0.25 of X has reacted, the ratio is 1:2. So how much of Y would be produced? 0.5. Okay, so at equilibrium, how much Y do you have? 0.5 moles of Y. Remember, it's 1:2. When 1 mole of X reacts, 2 moles of Y is produced. So when 0.25 moles of X reacts, they produce double the moles of Y, which means 0.5. So you have 0.4 moles of Y at equilibrium. Okay. Now simply, you can see at equilibrium you have less of X and more of Y. So this option and this option is impossible because they show X and Y in the same amount at equilibrium. So A and B are wrong. Now we are left with option number C and option number D. Okay, remember, let's calculate Kc. What is the expression of Kc? Concentration of the product raised to the power of coefficient upon the concentration of reactant at equilibrium. Pick up your calculators, do it. 0.5 square upon 0.25. You will see the answer will be 1. So the correct answer is C, because the expression of Kc is 1 and you have the concentration of X at equilibrium is 0.5 and the concentration of Y at equilibrium is 0.25. So the correct option is option number C. Question 9. Okay, now this is a slightly different one. In this question, there's this reaction given and Kc for the reaction. Kc for the reaction is given and the Kc for the reaction is 4. With the help of that and this information that you have 1 mole of ethanol and 1 mole of ethanoic acid are allowed to reach equilibrium, what is the number of moles of ethyl ethanoate formed? Now you have to find the number of moles of ethyl ethanoate. See, once again, I've made this format. See, you have 1 mole of ethanoic acid and 1 mole of ethanol and nothing of the product. And assume you have X moles of ethyl ethanoate at equilibrium. So remember, Of course, all the ethyl ethanoate is produced. So that means X moles of ethyl ethanoate are produced. Now, since ethyl ethanoate and water are in a ratio of 1:1, so means X moles of water are also produced. And hence, there are X moles of water at equilibrium. So you have X moles of ethyl ethanoate and X moles of water at equilibrium. Okay, I'll just put a dash because reactants are not produced in this equation. Okay, now see. If we say that 1 mole of ethanol produce 1 mole of ethyl ethanoate, the ester. So if you have X moles of ethyl ethanoate, how much would ethanol be reacted? X. And similarly, X amount of acid will be reacted. See, simple. We say 1 mole of ethanol produces 1 mole of the ester. So if you have X moles of ester, then means X moles of alcohol has reacted and X moles of the acid has reacted. So what is the amount of alcohol and acid at equilibrium? 1 minus X. 1 minus X, because initially you had 1 and X had reacted. So what is the amount which remains at equilibrium? 1 minus X and 1 minus X. Okay. Okay, now let's put all these values in the expression. Expression of Kc is concentration of product. Concentration of product. This is the product upon concentration of the reactants. Upon the concentration of the reactants. Okay, upon the concentration of raised to the power of the coefficients in the balanced equation. So the expression of Kc, concentration of the product upon, these are the two products, upon the concentration of the reactants raised to the power. Now all the coefficients are 1, so all the powers are 1. Okay, let me now substitute the values. In the question, Kc is given as 4. We just worked out the equilibrium amount is X. For the ester, this is C2H5. Okay. X for water, 1 minus X for the acid, and 1 minus X for the alcohol. Now simple mathematics, I can say X square and 1 minus X square. Now I'll take root on both sides. See, that's what I'm taking, root on both sides. So what do we have? We have X upon 1 minus X is equal to 4. I'll just simply solve this further. So X is equal to 4 into this. X is equal to 4 minus 4 minus 4x. Pardon, this will be 2. Okay, so I'm sorry, the under root is 2. So this is 2 minus 2x. We'll have x plus 2x is equal to 2. 3x is equal to 2. So x is equal to 2 upon 3. That's your answer for x. So 2 upon 3. The option is B. Right? The option is B because the amount of, they say the amount of the number of moles of ethyl ethanoate formed is 2 upon 3. Okay, the last question in this lecture. And gaseous iodine is heated with hydrogen at 450 and equilibrium established. Okay, now remember the delta H is positive, so the forward reaction is endo and the backward reaction is exo. Okay, now this says what change of conditions will cause purple color of the equilibrium mixture to become paler. Remember, purple color is of iodine. So if we say that purple color becomes paler, actually it means reaction shifts forward. So actually the question is saying which of the following changes will actually shift the equilibrium forward. Okay, let's check. Decrease in pressure. Okay, now remember, when you decrease the pressure, equilibrium shift toward the side with more number of moles. Now remember, how many moles do you have on the reactant side? You have 2 moles on the reactant side and you have 2 moles on the product side. So it won't actually shift backward. So option A cannot be correct. Decrease in temperature. Okay, when you decrease the temperature, then exothermic reaction, which is backward reaction in this case, is favored. Remember, exothermic, when you decrease the temperature, then exothermic reaction is favored, which in this case is the backward reaction. So you do not expect B to be your answer. Increase in pressure. Once again, since the moles of the reactant and products are equal, therefore increasing pressure would not actually shift the equilibrium forward. The correct answer is D, because when you increase the temperature, then endothermic reaction, which is the forward reaction, is favored. When forward reaction is favored, then iodine will convert to HI and the purple color fades. So the correct answer is D, increase in temperature.